In this session, we are going to discuss about priority queues and heaps. First, let's try to understand what a priority queue is. So, you must have heard about priority scheduling in operating system. So, talking a brief about it, in priority scheduling, so basically operating system, what it does is, if it always looks for a priority that is it will always looks for a process that is of highest priority, and that highest priority process is assigned the CPU. Now the thing is, there must be a data structure which supports this operation of finding the process with highest priority. So this whole process of finding the highest priority process should be efficiently handled by some data structure. Now, there are many scenarios in which we need to find the maximum and minimum element. So, priority queue is a data structure that supports this operation, finding maximum and finding minimum elements. So let's see what are the main priority queue operations. Insertion of an element, finding maximum or minimum element. So let's say there is a particular code or there is a particular program that needs to find maximum minimum element lot number of times. So if this particular operation, finding maximum or minimum, is not efficient, this will lead to slow execution. So there should be a data structure that efficiently handles this particular operation. Next we have deleting minimum or maximum element. So we are looking for a data structure that supports this operations. So we have seen various data structures till now. We have seen arrays, we have seen linked lists, we have seen trees. So let's try to see that how do we use these data structures such that these operations are handled very efficiently. So let's say I try to implement priority queue using an array. So I have an array and I try to implement priority queue using this array. So what will be my time complexity for insertion in an array? It will be O of n. Deletion will be O of n. So this deletion means deleting minimum or maximum will be O of n. So if I have to insert the element, I'll just insert it at the end of the array. But for deleting minimum or maximum element, I'll have to see that which is the particular element, which is minimum or maximum. So I'll have to go through the whole array to find the minimum or maximum element. So this will be the time taken. Now let's say I take linked list. I implement priority queue using linked list. So let's say in this linked list, what I will do is that I will try to insert each element in a sorted order. So my insertion will take O of n, and in case my elements are inserted or my elements in a linked list are in sorted order, so my deletion or insertion of minimum or maximum element will take O of 1. We have another option of balanced binary search tree. Let's say I use balanced binary search tree for implementing these operations, so that the insertion, finding minimum and deleting minimum and maximum operations are possible. So we know that these operations are possible using balanced binary search tree. Okay, before we see for balanced binary search tree, let's see for BST only. So for BST, the average time taken for insertion and deletion will be log of n, as well as the time taken for finding minimum or maximum will be log of n. We have seen in the previous chapter. Now, this will be the average case scenario. The worst case scenario can be O of n as well. In balanced binary search tree, the best case scenario will be O of log n. So we have seen that if we go on to implement priority queue using array or linked list or balanced binary search tree or binary search tree, we get these time complexities. Now, let's say I introduce a new data structure. I introduce heaps. So let's see, first let's try to understand what heap is, and then we will see that how do we go for finding minimum maximum element and insertion, and inserting a new element and deleting a new element. First, let's try to understand what is a heap. Finding a maximum element takes of one time. Insertion and deletion takes O of log n in worst case time scenario. So you can see that this is better than rest of the data structures that we saw. So let's see how do we come up with this time complexity, what is a heap and what are the properties of a heap. So a heap is nothing but a tree with special properties. So what are the special properties? First property is all the child elements are either greater or lesser than the parent element. Second property is that all the elements or all the leaf nodes must be at height h or h minus 1, which I am saying that this should be a balanced tree. Now, let's take an example of two trees. Okay, so we have two trees here. So how do we know that this particular tree is a heap or not? And one more thing, in this particular discussion, we will generally talk about binary heap. So as the name suggests, binary heap means a particular parent will have only two children, maximum of two children. So in this particular case, let's see that whether these properties are getting satisfied or not. For this particular trees to be heap, these properties should get satisfied. So as you can see that here, all the child elements should be either greater or lesser than parent. So in this particular case, one more thing. If I am saying that either greater and lesser than parent, which means that if this particular element is greater than the child elements, which means that rest of the tree should also follow the same norm. Like either all the child elements should be greater than the parents in a particular tree, or all the child elements should be lesser than the particular, lesser than the parent. It should not happen that some are greater, some are lesser. Either it should be that all the children are greater, or all the children should have lesser value than the parent. So in this case, as I can see that 2 and 3 are greater than 1, 4 and 5 are greater than 2. So this is a heap. I can qualify this as heap. And also the leaf nodes are at height h or h minus 1. In this particular case, all the child elements are lesser than the parent. So you can see that 4 and 3 are less than 5, 2 and 1 are lesser than 4. So this also can be qualified as heap. Now, there are two kinds of heap. So let's say I have this heap here and I try to represent this heap using an array. So I can think that this is the 0th index. I can just write it in array like this: 17, 13, 6, 1, 4, 2, 5. So this will be the 0th index, this will be 1, this will be 2nd index, this will be 3rd, 4th, 5th and 6th index. So these are the indexes and this is my heap. I am representing my heap using an array. Okay, so what will be my structure for this? I will have an array. I will have the count. Count is the maximum number of elements in the heap. We have capacity. Capacity is the maximum number of elements that a heap can accommodate. So this count is the number of elements that we have currently in the heap. So let's say the maximum capacity is 8. The capacity is 8 and as of now I have 6 elements in the heap. So this count contains 6 and capacity contains 8. And then we can also have heap type. I can store this as 0 or 1, 0 for max or 1 for min as we go as convention. So this will be my structure for heap. Now, so let's say this is my structure. So one thing to note in this particular case is when we have an array that is representing heap, one thing we can note here is, let's say this is a node and I have to find the parent element for this particular node. I have to know that okay, this is the index and I want to know that at which particular index the parent of this particular child is located. So for finding the parent, if I do this particular thing, let's say this is 4, I get 1, and I can see that the parent of 4 is at index 1. So for any element I can get the parent of that particular element I using I minus n by 2. So this is how we get the parent of element. So now let's say I am given the index of a parent. I have index of the parent. How do I know what is the index of the child? I can, obviously the parent can have maximum of 2 children. So the children will have indexes 2 into I plus 1 and 2 into I plus 2. So in this particular case, the parent is at index 1. So if I do this particular operation, 2 into 1 plus 1 and 2 into 1 plus 2, this gives me 3 and 4. And we can see that the children of this particular node is located at index 3 and 4. So this is a auxiliary operation. Given a child element, you can easily find the parent of that particular child, and given a parent, you can easily find the children of these particular element. Now, how do I find the maximum element? So we know that the maximum element will always be at the top in case it is a max heap. So let's consider that we will be talking about max heap throughout the session. Minimum heap will have the similar operations. It's just that the basic thing will change, that we will have the minimum element at the top of the heap, and we have to implement minimum heap or maximum heap depends upon the problem statement, what kind of problem are we getting. So given the particular heap, how do we know what is the maximum element? So we know that maximum element is always at the top. So let's say this is our heap. So the 0th element of this particular index always gives me the maximum element. So these are the small operations that you need to know and that we will be using as we go through the code.